Hello! In this video, I'll be explaining 4 competitive programming problems. These come from the most recent Leetcode contest, so if you want to watch me solve them live, here's a time lapse of me solving them live in 10 seconds. Okay, so I'm going to be explaining all 4 of these problems. The first one's going to be relatively easy, the middle 2 are going to be a little bit harder, and the 4th problem is going to be the hardest of them all. But these problems aren't too difficult for competitive programming in general, I guess. But yeah, I might as well explain these. So, problem 1, matrix diagonal sum. Given a square matrix MAT, return the sum of the matrix diagonals. Only include the sum of all the elements on the primary diagonal and all the elements on the secondary diagonal that are not part of the primary diagonal. So this is a really easy problem. We just have to mess around with a bit of math and off by 1 stuff. So we just take all the coordinates that have x and y being the same, and then we take all the coordinates that have x and y adding up to n minus 1, because that represents the secondary diagonal. But we also need to make sure that when we're checking the secondary diagonal, we don't include any points that are already part of the first diagonal. So that's why this if statement is here. We just check that the y coordinates are not the same when we're looping through the x. So this is just a really easy problem. I mean, you just have to find out the coordinates, and yeah, it's not that hard. Problem 2, number of ways to split a string. Given a binary string s, we can split s into 3 non-empty strings s1, s2, and s3. Return the number of ways s can be split such that the number of characters 1 is the same in s1, s2, and s3. And the answer may be large, so we have to return it modulo 10 to the 9 plus 7. Okay, so this problem, there were a few edge cases. I mean, okay, maybe there's like one. Okay, so I guess I should just explain the edge cases first. So basically what we're doing is we're given a binary array, binary string, and so for example, it has a lot of 1s and some 0s, right? This string has a total of 6 1s. We need a multiple of 3 count of 1s, because otherwise we can't split into 3 strings with each one having the same number, right? Because that means that the number of 1s has to be divisible by 3. So in this if statement over here, we just check that the number of 1s is divisible by 3. After that, okay, we have to see if it's all 0s, because if it's all 0s, that messes some of our computation up, because what we're actually doing here is we're taking, for example, if we take this string, each string has to have a number of, has to have 2 1s in this example. So the first S1 could have this, I'll draw it on top, I guess, could have this, or this, or this, or this, right? Because all of these contain 2 1s. But after that, S1 cannot include this one. So S2 has to include these 2, and S3 has to include these 2. But S1 has a lot of choices, because it can split S1 and S2 anywhere between these 2 1s, and that's valid. But if it's all 0s, that messes our computation up. So if there's a bunch of 0s, this still passes our first test because there's no 1s, and 0 is a multiple of 3. But basically what we need to do here is we have n minus 1 places where we could split the strings. And we need to choose 2 of these places, because taking 2 split points divides the whole thing into 3 parts. So we need to choose 2. And if you know combinatorics, you know this is just n minus 1 choose 2. But to explain it, I'll just say the first one, we have n minus 1 choices. So we choose this one, for example. And we have n minus 1 choices for the first one. The second one, we only have n minus 2. So we have n minus 2 choices. But also, note that choosing this one first and this one second is the same as choosing this one first and this one second. So we actually need to divide by 2, because each of the cases we counted was actually counted twice, because we counted it because order doesn't matter, but we counted it with order. So we need to divide by 2. And yeah, so if it's all 0s, then we need to check for that. Okay, so that's the all 0 case. I actually got a penalty because I forgot to take it mod whatever. But okay, so after that, we're going to do something like this. We're going to do something like the thing I described earlier. So let's just use the same string. Actually, maybe we should use a different string. First, we know there's 6 1s. We're going to calculate that. So 2 1s per string. And how do we find the possible split points? Well, we loop through until we hit 2 ones. So this has 2 ones, and then we keep going until we hit another one. So we keep going until as long as it's zeros, and then we know that we can split the string between S1 and S2 at any of these points. So we know that there are 4 possible split points between S1 and S2 because we found S1, we found the possibilities for S1, which are all the way from here, just this 101, because it has 2 ones, and then all the way until it has 3 ones. Well, right before it has 3 ones. Okay, and then for S2, we just take a look. It can start here, right? Because it has to be, it has to include at least 1 1, right? So S2, it can start here, and then it has to contain these 2 ones, but then it can just keep checking until it hits another one. So this could be S2, and then we find that these are the possible split points between S2 and S3, and then S3 has to be the remaining ones. So we actually only need to check for 2 split points, the split points between S1, S2, and S2, S3. So we find that there are 4 split points between S1 and S2, and 4 split points between S2 and S3, and this means that we have 4 times 4 equals 16 total possibilities. And that's exactly what we do here. We just find possible split points by counting the number of ones that are in that substring, and that's it. So yeah, just in these problems, you have to think about it for a little bit, but don't forget to take it mod 10 to the 9 plus 7. Problem 3, shortest subarray to be removed to make array sorted. Given an array integer r, remove a subarray from r such that the remaining elements in r are non-decreasing. A subarray is a contiguous subsequence of the array. Return the length of the shortest subarray to remove. Okay, so for this problem, we can only remove 1 contiguous subarray, and this means we're either going to have to remove it at the beginning. This means we're either going to have to remove it at the beginning, at the end, or in the middle. And if it's in the middle, that's relatively simple, but we also need to consider if it's going to be removed at the beginning or the end. So okay, so here's what we do. I should take an example. So for example, we could have something like 10, 11, 12, and then 1, 2, 3, and then 15, 16, 17. In this case, we know that we can include both the prefix and the suffix if we just remove the middle part, because if we remove the middle part, then 15 would still be greater than 12, and this would be valid. But if we had something instead like this, 15, 16, 17, 1, 2, 3, 10, 11, 12, then we need to go into our other case. This is the prefix and this is the suffix. So this first case over here, that's this right here, because we just removed the middle part if 12 can go directly to 15. But in the second case, 17 cannot go directly to 10. So that's where we need to do a bit of binary search. So how do we do binary search? Well, we're going to look at how much of the prefix we can include and how much of the suffix that implies we can include. And this is actually helpful, but not in this case, because we have to either include the prefix or the suffix, because there's no common ground here. So if we did something instead of like this, 15, 16, 17, 1, 2, 3, and then we had 10, 15, 16, this would be okay. So this is actually where the binary search comes in helpful. So if we take the 15, if we only take 15 from the suffix, how much of this, if we only take 15 from the prefix, how much of the suffix can we include? Well, we can include 2 of the suffix. So that gives us a best value of 3. Okay, well, let's consider. What if we take 2 from the prefix? How much of the suffix can we include? Well, we can include 1. So that's also a best value of 3. If we include all of the prefix, how much of the suffix can we include? None of it. But that still sums to a 3. I guess this isn't the best example for binary search. Maybe something better would look like 15, 16, 17, 1, 2, 3, 10, 15, 15, 15, 16, right? Because then if we include the 15, then we can include all of this. But if we include the 16, and that would sum to 5. But if we include both 15 and 16 from the prefix, then we can only include 16 from the suffix, and that would only give us 3. So binary search, because this is sorted, we can search for the place that we can search for the earliest place that we can include, and everything else we discard. So we're looking for the minimum possible place to discard, so we're looking for the maximum prefix and suffix that we can include. And yeah, I used min function here because that's the minimum we can include. But yeah, and this is the binary search part. Python has a great built-in library for binary searching arrays. It's called bisect. But this is only for sorted arrays. It doesn't work for like more general binary searching problems. But yeah, that's all the cases. Yeah, we just determine, so in summary, we just determine the longest prefix that is sorted and the longest suffix that is also sorted. And then we determine how much of the prefix and the suffix we include, and then we just take out everything else and return that. So yeah, this problem involves a little bit of binary search. Problem 4, count all possible routes. You are given an array of distinct positive integer locations, where locations I represents the position of city I. You're also given integers start, finish, and fuel, representing your starting city, ending city, and the initial amount of fuel you have, respectively. At each step, if you are at city I, you can pick any city j, such that j is not I, and j is a valid index, and move to city j. Moving from city I to city j reduces the amount of fuel you have by locations I minus locations j, absolute value. Please notice that, absolute value. Okay, so notice that any fuel cannot be negative at any time, and you are allowed to visit any city more than once. Return the count of all possible routes from start to finish. And yeah, return a mod 10 to the 9 plus 7. Okay, so this problem, if you read this, you should know immediately that it's dynamic programming, right? Because, so the states is how much fuel you have and which city you're at. And it's really easy to transition between these states because moving your location directly influences how much fuel you have left. So this is actually a really simple DP problem. And I like it when Leetcode includes DP problems at the end of their contest because it makes me more motivated because I can actually solve these. So yeah, okay, so this is just a DP problem. What more do I have to explain? So yeah, that's great. Okay, that's 4 competitive programming problems explained. I hope those explanations were clear. I hope they help you out. And yeah, I did okay on this Leetcode contest. I got 339. I could have done better if I didn't get all those silly mistakes, but I think it was fine. So that's it. Thanks for watching, and I'll see you next time. Goodbye.